This is lesson 7.6. In addition to these warm-up problems, I just asked students to also identify which special segment is shown in each set of similar triangles. So it says find the value of x in the similar triangles below. All right, I'm going to highlight the special segment here. All right, and number one. What do we call that special segment I just highlighted? Median. Median, right? From the vertex to the midpoint of the opposite side. Okay, these are medians. So what we learned is that in similar triangles, whatever the scale factor is of all the corresponding sides, the medians are also proportional to that or have that same scale factor. Okay, so here they're showing me a set of corresponding sides with the 32 and the 20. So if I write that as a ratio, I'm going to go 32 to 20. That's going to be proportional to the length of their medians as well. Okay, so since I started with 32, this bigger triangle, I'm going to have to do x up top to 16. All right, so that's how you should have set up the proportion. Now you can just cross multiply right away. You can reduce the scale factor if you want, then cross multiply. I reduced first. Either way, let's see. I did get a decimal. That's okay. You could either write x as 128 fifths, but since we're talking about length of a median, probably 25.6 would be a better answer. You should also be checking that your answers make sense. So the length of my median in this triangle on the left here, does it make sense that it's larger than the median in the triangle on the right? Yeah, it has a longer side, right? It's a bigger triangle. So that answer makes sense. Okay, there's number one. Number two, which special segment is shown here? Altitudes. They're altitudes from the vertex perpendicular to the opposite side. Same thing. The ratio from altitude to altitude in similar triangles is proportional to any set of corresponding side lengths. The only thing that was different here is they actually gave me the length of the altitude. So I'm just going to start, me, I like to start with like the bigger ones. So the ratio of the altitude of the bigger triangle to the smaller triangle, 5 to 8, is going to be proportional to the corresponding sides, which they're showing me 18 to x. Okay, obviously you don't have to have this exact proportion. Here, when you cross multiplied, I got x to be 9.6. All right, any questions on those? All right, 3 was similar. Which special segment is this? Angle bisector. Thank you, Matthew, for participating in my lesson. Angle bisector. So same things as median and altitude. The lengths of those are also proportional to any set of corresponding sides. All right, so let's set up the scale factor here. 56 to 42. That's proportional to, let's see, since I started in this triangle, 40 to x. All right, that reduces to 4/3. So you should get 30 for that one. Okay. The other thing we learned in 7.5 was if we just have any old angle bisector in a triangle. Oh, Matthew, will you let me in? Hi, honey.
Hey.
Are you going to observe me?
Yeah.
Oh my gosh, I'm nervous. Okay. Okay, you guys, answer my questions for a change. Make me look good. It's my face, right? I feel a little flushed. Okay. This one's different because we don't have similar triangles. We don't have two sets of triangles. We just have one triangle. So the other thing we learned is that The angle bisector splits this third side into proportional lengths of the opposite two sides. All right, I'll highlight this for you. This length right here is obviously 10. Okay. What's the blue?
14.
Good. Okay. So the ratio of those two pieces, again, and how you set up the ratios, up to you. But if I go 14 to 10, if I write it that way, I have to set up my proportion using the other side that touches that segment of 14. So I would have to write it as x to 28. Okay, or you can have that flipped, as long as you're consistent with your proportion. This time when you cross multiply, I reduced first. So 39.2, is that what you guys got?
Sure.
Yeah.
Yes, because your
I
teacher
got
is
it.
awesome, right?
I did it a different way.
Did you flip these? Or did you set up the ratios like this to this?
Yeah.
Yeah, you can do that.
Oh.
Nice. I like it. Okay. So, if you looked at the title of this lesson, Similarity Transformations, we've talked about 3 types of transformations in previous chapters, but they were congruency transformations. Can anyone list or give me one of the 3 transformations we talked about? No pressure, but my 7th hour got all of them. Reflection was one.
Rotation.
Translation and rotation. Nice. Okay, so we did this with triangles. We did it with different shapes like rectangles. But these ones were congruency transformations because every time we did a rotation or a translation of like the slides or a reflection, did the size of the shape change? No, they were always congruent polygons, whatever shape they were. All right. So today we're going to look at a new type of transformation where the size does change and it forms 2 similar triangles or rectangles. Okay, it's called a dilation. So it's a transformation that either makes your shape bigger, which we call an enlargement, or smaller, which we call a reduction. Proportionally, leaving me with 2 similar shapes. Okay? So that's basically what that definition says. Transformation that either enlarges or reduces the original figure proportionally, leaving you with similar figures. So similar, meaning it's the same shape, just a different size. Okay. Now we could kind of look at this picture I gave you 2 different ways. If I said ABC, and it's nice because mine are color coordinated, I know yours aren't in your notes, but if I said ABC was my original figure, original shape, and I dilated to form this image, this green image, do you guys think that would be a type of an enlargement, dilation, or reduction? Why? It's getting bigger, exactly, right? You guys know when you get like your pupils dilated, like they get bigger or smaller? Okay. I could also look at this as if the green was my original and I dilated it to form the image of the blue, then I could call it a reduction. Okay, so you do have to be careful with which one's your original and which one's your, what we call our image, kind of your after. Dilations are done usually from a fixed point. In geometry, we're just pretty much going to use the origin for that. It's usually the origin, not always. But you can kind of see that right here, the center of dilation. What we're more going to work with is the scale factor because we've been talking a lot about ratios and proportions and scale factors of similar polygons. So the 2 types, whether it's going to be an enlargement or a reduction, depends on what your scale factor is. They use the variable k for our scale factor in dilations. So how we're going to write our scale factor is as a ratio, this one's important, of the image after we perform the dilation. So after the transformation, that's going to go on top. A ratio of that to the original always goes on bottom for these ratios. Okay, we'll do a couple examples and I'll kind of explain why we do it that way. So you just want to write your scale factor as a ratio of the new figure to the original. Okay. So let's look at our two types of dilations a little more in depth. Starting with enlargement. And the words are very similar to what they mean in like everyday language, right? Enlargement means getting bigger, reduction means getting smaller. Okay. So if our scale factor, which we're calling K, that's what they're showing right here, if K is greater than the number 1, then the dilation is considered an enlargement. Let's think about why this makes sense. So here they're saying our original triangle is triangle FGH. If I had a scale factor of 2, what that means is all my side lengths would double, right? Is that going to make your triangle bigger or smaller? Bigger if you double everything, right? So that's a scale factor that's larger than 1. Going the other way, if I shrunk each side by half or times everything by half, let's look at this trapezoid. So if I took all those lengths, times them all by half, it's going to make it smaller. Yep, so then if the scale factor is less than 1, but the scale factor still has to be positive. So how we say that in math is that it has to be greater than greater than 0. That means positive, but still less than 1. So all those numbers in between 0 and 1, like 1/4, 1/2, 3/10. You have a question?
Is that supposed to say K is greater?
Yeah, I noticed that. I don't know why. I saw it from the textbook. That's supposed to say greater than 1. Thank you. Then the dilation is a reduction. Yes, Alejandro.
In theory, what would happen if it was negative?
You can't have negative scale factors.
But if you could.
We can't have negative side lengths of a figure, right? Can't have negative distances.
Fourth dimension.
How would you stop?
You can look into that.
I will.
All right, guys, that's really all we're doing today, are these two big ideas. Obviously, we'll do some example problems here, but those are our new vocab, new concepts for us. But you already know what scale factors are, and you know a lot about ratios, so not bad. Alrighty. Determine whether the dilation from A to B, and I know, again, yours aren't color coordinated, but you can see which one's A and which one's B. So it's saying from figure A, meaning A is my original, A is the OG, to figure B is an enlargement or a reduction. All right, so if I'm starting with A, transforming to B, enlargement or reduction?
Enlargement.
What do you guys say?
Enlargement.
Why?
It's getting bigger.
Exactly. Enlargement. Good.
Wow.
It's that easy.
Brain power.
So difficult.
Enlargement. If you want to write this down, you can. B is bigger than A. Okay. So that answers their first question. It says, then find the scale factor of the dilation. So we're just trying to find like a pair of corresponding sides and then writing that ratio to find the scale factor. So I always pick ones that are easy to find the length of. Now this trapezoid A, this base right here, 1, 2, 3, 4, that is a length of 4. That one's easy to calculate. Its corresponding side in its image, or this other trapezoid, 1, 2, 3, 4, 5, length of 5. You could also use these ones. If you wanted to use these distances, you'd have to use the distance formula, or you'd have to use Pythag and make a little right triangle. So I'd pick ones that are easy to calculate, but I think there is one on your homework where they're all like slanted and you might have to use distance formula. Don't worry, you guys know how to do that. You're pros at distance formula. Okay, so as I mentioned before, when we set up these scale factors, we always want to write it as a ratio of the image after the dilation to the original. That's important. We have to write it that way in order for this to hold true, that if that scale factor is larger than 1, it's going to be an enlargement. So the length of the image after the dilation, that's B, is 5. Want to write as a ratio of that to the original is 4. And does this make sense that we have an enlargement, aka is that scale factor greater than 1? Yep. Okay. So our answer makes sense. If you want to write that down, that number should be greater than 1 if you're saying that that's an enlargement. And that can be a way to check if you set it, that ratio up correctly. Does that make sense? Okay, I'll try another one. Okay, so again, we're going from A to B, but be careful with this one. A is on the right this time. So we're going from A, my blue one, to B. Enlargement or reduction? Why? Exactly, it's getting smaller. B is smaller than A. All right, so scale factor. We have a couple easy lengths we could count here. You could either do like the bases of this right triangle. I'm gonna do that. Or you could do these this leg right here. That's 1, and that's 3. All right, so I write my scale factor. I need it to be the ratio of the image after the dilation. So that's B, that's my green one. 1, 2, the original goes on bottom. 3, that makes sense because I know for reduction, my scale factor should be in between 0 and 1. Is 1/3 in between 0 and 1? Yes, it is. Okay, not bad. Let's try another type of problem. A photocopy of a receipt is 1.5 inches wide and 4 inches long. By what percent should the receipt be enlarged so that its image is 2 times the original? What will be the dimensions of the enlarged image? Okay, I'm going to draw a picture here. So my original receipt, it looks something like this, is 1.5 inches wide, 4 inches long. We want to enlarge this so that its image is 2 times the original. There's your scale factor. All right, so let's look at the length first. What's 4 times 2? 8. And you can write this down if you want. What's 1.5 times 2? 3. So this answered their second question. What will the dimensions of the enlarged image be? 3 inches wide by 8 inches long. However you want to write that, you can write it out in words if you want, or you can write it like that. Make sure you include units though, 3 inches and 8 inches. There are some new dimensions. Here's a good question. I'm curious if you guys think you know this. What percent would we be enlarging it? I know I'm timesing my scale factor by 2. Anyone have a guess at what percent that would be? Alejandro, guess?
100%.
100%. Okay, other guesses? 200%. Okay, other guesses?
300.
500%. Okay.
Sold.
Why do you think 100?
Because you're adding 100% to it.
Okay.
Or yeah.
Okay.
100% just be the same thing because like 50% would
I
be
think
more.
I think it is 200%.
Ooh, you convinced him.
Yeah.
Okay, let me phrase it this way. Let's say I had 5 of you in this class on a Monday.
Sure.
Monday, 5 of you showed up. On Tuesday, I said 100% of the people returned. How many people would come back?
5.
5.
Okay, so it was.
What if I said 200%? It'd be double. Exactly. It'd be those 5 plus another 5. It'd be 10. It'd be double. So when we're doubling, that's really 200%. Do Do you want to add to that, Mr. Reynolds? I feel like you guys do a lot with percent and. Did you like my example? Okay. He's also a math teacher.
I thought he was a principal.
1 + 1 = love.
It's 2 + 2. 2 + 2 = love.
Do
2
your
+ 2 also equals fish.
Do your line
Get it right.
segment.
Oh, you wanna? Hey, Mr. Reynolds. Oh, I'm recording this, by the way, too. It's gonna be on YouTube later. If you were a line segment, you'd be a QT. Okay. All right, we got a couple more prompts to do here. Sorry, so distracted. So the reason why he's here, if you guys didn't know, I don't know if you heard me say this. He's going to school right now to potentially be a principal. He's getting his principal license, so he has to do 2 full observation days in other schools. So he teaches in Lancaster, but he has to observe an administrator a whole day. So he's doing it here today, basketball tomorrow. So he was observing Libby's mom. I'm teaching. So you can ask him. Maybe he can help you. Algebra 2. All right. Is that my phone?
Oh, sweet.
Think what way? So much going on today, right? I'm excited. Graph the original figure and its dilated image, then verify that the dilation is a similarity transformation. All right, here's the original. I'm going to graph this one in blue like I have been. 2, 3, 0, 1, 3, 0. A, B, C. What shape is this? Triangle. Good. All right, its image. Image means the figure after we perform the dilation. Its image is located 4, 6, 0, 2, 6, 0. And this is D, F, G. Okay, so my original is blue. Oh my gosh. Image is green. Enlargement or reduction here?
Enlargement.
Enlargement, good. Yep, enlargement. It's getting bigger from blue to green. All right, here's the part that's a little bit more work. They want us to verify that this dilation, specifically this enlargement, is a similarity transformation. So they basically want us to verify that these 2 triangles are similar. Okay, so here's where I put this little notice in red for you. I said, if it's a triangle, we can use these theorems we talked about, side-side similarity, side-angle side, or angle-angle similarity. Otherwise, if it's not a triangle, you have to show that all the angles are congruent and all the sides are proportional. So since this one is a triangle, we can use side-side sim, side-angle side, or angle-angle. But do we know any angles? No. The only way that would really happen, you can mark this down if you want, is if it forms a right angle on the graph. So if you know there's like a 90-degree angle, then you could maybe use one of these 2. But for now, we don't know any angles, so we have to use side, side, side. Which means I have to find the lengths of all these sides. Which means I get to use our good friend distance formula. Don't worry. You guys get plenty of practice with distance formula in your homework, so I found them for you. Yes. All right, let's start with the original. Start with AB. All right, folks. I did the distance formula, and I got the square root of 8. Now, what I'm going to tell you is 2 things. 1, we need to practice writing these as simplified radicals anyways. And 2, it makes these problems a lot easier if you do that, if you write them as simplified radicals. Okay, so the square root of 8 reduces down to 2 root 2. As I mentioned, you'll get some more practice in your homework. Okay, AB corresponds to FD, so I'm going to write that one right underneath it. That distance, I got the square root of 32, so it was 4 root 2. All right, I'm just going to keep working down my triangle here. So then AC, let's see, what did I get for that? Square root of 10, no perfect squares going to 10, so that's simplified. DG, I got 2 root 10, so I must have got the square root of 40 there. Simplified that radical down to 2 root 10. All right, CB. I got the square root of 10. Ooh, isosceles triangle. GF. I got 2 root 10. Okay, so yes, you will have to calculate all those distances, unless they're nice, like if it forms like a right triangle, and you can obviously just like count. So we haven't really shown that they are similar yet. We have to show that all their corresponding sides are proportional. All right. Now, remember how we write these dilation scale factors. I always want to write it as a ratio of the dilated length to the original. So when I set up this ratio between these corresponding sides, A, B, and F, D, I want to do the green one on top, the ratio of that to the original. So you could write like AB and FD if you want in your notes to see where we're getting these from. Okay, let's go over the algebra here. This is really the same as 4 over 2 times root 2 over root 2. Anything over itself is just a big old 1, so those cancel. That reduces to 2. Okay, next set of corresponding sides, DG and AC. Again, original we want on bottom when we're finding the scale factor with these dilations. That's the same as 2 times square root of 10 over square root of 10. It's really just a big old 1. That's 2. So far, so good. They're proportional. Or you could say they have the same scale factor. Last one. We got to show all 3 if we want side, side, side similarity. GF to CB. Those are the same. As we said, this is an isosceles triangle. That's also 2. So what we can say is that our triangles are similar. So I'll go my original ABC is similar to, there's our symbol for similar to, its image DGF by side to side sim. The only other thing I want you guys to write down here, sorry, one last thing. And this is an enlargement with the scale factor of 2. Okay, we only got one more to go. Same type of problem. Any questions?
Thank you.
Thank you. I was getting nervous up here, sweating. I did good, right? Thanks for answering my questions. All right, one more. Then we're done. Same setup. But this time, my shape is not a triangle. Let's graph to see. 2, 1. Oops. 2, 1. 4, 1. 2, 0. 4, 0. What shape is this?
Rectangles.
It is going to be a rectangle. I, J. Okay. After you get that plotted, go ahead and plot the image. Okay, so your original is blue, image is green. Enlargement or reduction?
Enlargement.
Enlargement again. Yep. All right, so same directions. They want us to verify that these are similar shapes, aka a similarity transformation. That's just saying, show that these are similar. So I copy and pasted that same notice. If it's a triangle, it's not a triangle. So we can't use that. So we have to show that all the angles are congruent. But this is a rectangle, so all the angles are what?
90 degrees.
90 degrees. Boom. Done. All angles are right angles, so they're 90 degrees. So we got to show that, and we have to show that all four sides are proportional. Now with rectangles, because the opposite sides are always congruent and parallel, it's not too bad. And especially look where these look where these rectangles line up, right on vertical and horizontal grid, so we can just count. Okay. So I'm just gonna go down here and do all the blue ones. So GI, GH, HJ, JI. Okay, so just counting here, GI is obviously 1, and so is HJ. Both have a distance of 1. What about GH? 2 and 2. Okay, I'm going to put the corresponding ones over here for the image. So GI corresponds to SQ. GH, the top piece, corresponds to QR. HJ is RT. JI is TS. Okay. SQ and RT are both 2. QR to ST are both 4. All right, so at least we didn't have to use distance formula there for this one. At least they were all easy to calculate. So again, we just have to show that these are all proportional. So I'm going on my list here. Now, from the image to the original is how we want to write this. So I'm going to do my green ones first. So 2 to 1 reduces to 2 for the first set of corresponding sides. QR to GH, 4 to 2, also reduces to 2. So far, so good. Next set, you have to show all 4 of them. RT to HJ, 2 to 1, 2. TS to JI, 4 to 2, 2. Okay, done. We have to show all the angles are congruent, all the sides are proportional. So, all else I want you to jot down is that rectangle GHIJ is similar to rectangle QRST, and it's an enlargement with a scale factor of what? 2. Makes sense that we got a number bigger than 1. That's all she wrote.
That wasn't always on.
So, just to give you guys a heads up though,
It is Tuesday.